Hi, in this video we will be going over the data logging and trace peripheral on our C29X devices. Let's talk about why data logging and tracing is important for real-time application code. In the following diagram we have some control loop that is controlling a motor. In this control loop we may have some control variables we would like to data log or trace during real-time execution. We may need to data log the control variables, sensor values such as temperature, pressure, with an ISR or loop. In most scenarios, if we were to data log many variables within an ISR loop, our CPU will have added overhead that may affect our intended real-time application code. Well, with the C29X CPU and the use of the DLT, we can avoid the CPU overhead and data log as many variables as we would like without impacting the overall real-time application code. The DLT allows you to set markers in your code to trace code execution and data log variables to an internal memory or export it out through a communication peripheral. The DLT provides timestamping, program count information, along with a few other flags when being used. Each C29X CPU will have their own DLT peripheral. Here's a quick one-slider summary of the features I mentioned in the previous slide. The DLT offers a non-intrusive way to data log critical runtime content and trace application code in real time. The main features of this peripheral are the following. There are two independent capture modes in which data logged information can store either program counter or timestamping of when data logs are reached. Interrupt generation and DMA triggering are possible from the DLT. Let's go over the DLT terminology that will be used for the rest of the video. Tags are used as markers in the code and allow you to trace your application code. So whenever we mention a tag, we are referring to the DLT tag instruction that is being data logged with information related to where you are in the code. Regs are used to data log the actual variables. The additional information that is packed with these data logs for tags and regs can be determined by the DLT configuration. The DLT configuration can either pack program counter or timestamp information along with the tags and regs being data logged. We'll talk more about what the additional information will look like when we talk about the data log structure from the DLT. How do we start and stop data logging? There are many ways to start and stop data logging, such as using the ERAD events or tags from the DLT, and you can use a combination of both. As mentioned in the previous slide, there are a couple ways to start or stop data logging, such as using the ERAD or tag filters. The following configuration shows a step-by-step of what is needed to enable data logging using tags. Tags can be used to signal a start or stop of data logging for the DLT. Let's walk through the steps. First, you would want to enable the DLT start and end base tag feature through the tag filter enable bit. Then you want to configure the tag filter start reference. Third, upon the condition when a tag is reached and tag matches the start reference that was configured in step 2, the DLT will start data logging. When the condition is reached when the tag matches the end reference, the DLT will stop data logging to the internal memory. These two conditions are similar for ERAD events or triggers. Now that we have enabled data logging, how do we read from the internal memory where we store the data logs? There is a memory mapped register in which we can read the DLT data logged contents from and transfer the contents to a bigger buffer or export it out of the device. The memory mapped register acts as a FIFO when storing data log contents too. How do we read from this internal memory or FIFO? Reading from the FIFO must be done in a certain way. To read all the data log contents, you should read the FIFO buff L first, then the FIFO buff H next. When reading the FIFO buff H content register, the next data log content will be pushed to the top. The DMA can be used to read from the FIFO. Let's now take an example piece of code where we will use tags and regs for data logging. In the snippet of code, we have a control motor ISR. There are two built-in compiler intrinsics that we will be using for tracing or data logging. The two built-in compiler intrinsics are built-in underscore C29 underscore datalog underscore tag for tags and built-in underscore C29 datalog underscore write for regs. In this control loop, we mark the beginning of our function with a tag and at the end of the function with another tag. In the middle, we datalog two registers which are speed and current from the ISR. When the following intrinsics are reached during execution, the DLT will store the data logging content to the internal memory. The tags will have their own specific format. Regs will also have their own format. In this DLT configuration, we are capturing the time when we reach our intrinsic. With each entry in the internal FIFO, we will see additional information such as tag, or the marker, and the variables that are reached during runtime. Let's look at the tag FIFO format. FIFO buff L holds timer 1's LSB, timer 1's overflow bit, the FIFO overflow bit, and if the LSB is a 1, then we know we received a tag. FIFO buff H holds information about the timer 1's MSB and the 16-bit tag entry used. In this control ISR, when the first tag is reached, the 16-bit tag entry would be 5, then at the end of the ISR, the 16-bit tag entry would be 2, as an example. Let's take a look at the reg FIFO format. FIFO buff L holds timer 2's information, timer 2's overflow, and FIFO overflow. The LSB is a 0, meaning it is a reg. FIFO buff H holds a 32-bit register content of the variable being data logged. Now that you have an understanding of the FIFO format for time capture mode, we can look at the PC capture mode. It follows the same idea of how to interpret the FIFO, but this time we are grabbing the program counter instead of the time capture of where the tag or reg were reached in the execution. Now, what is the source of timer 1 and timer 2? Timer 1 is used for data logging tags, the markers in the code, and are always absolute time since it uses the IPC timer as the source. Timer 2 is used for regs, or the variables being data logged. Timer 2 is used for the regs. Remember, regs are the variables being data logged. And timer 2 is sourced from the internal clock of the DLT. Timer 2 is relative to the previous tag or marker that it was data logged. Here is a quick list of additional features the DLT offers, such as connections to the interrupt controller and DMA. That wraps up this video on the data logging and trace peripheral on our C29X device. Thank you for watching.